So today I'm going to talk to you about the universe in infrared. And this is not necessarily an intuitive thing that people think about. So a lot of those space pictures that you see from the Hubble Space Telescope are all UV or visible light. And so all of those really pretty images of space are things that if you had eyes like Hubble, then you would be able to see out into the universe. And so there's all kinds of other things that we can see looking at different wavelengths. And I'm going to focus mostly on what we can do with infrared wavelengths of light. And so that's heat signatures in space. And so this is a really pretty image of a galaxy where it would look like the normal spiral galaxy you've always seen pictures of, but this is in the infrared, so it kind of looks like it's on fire, which is awesome. So if you were here at Astronomy Tap 18, I put up a slide. I'm not going to play the song for anybody who knows what I'm talking about, but I put up a slide to explain infrared. So I went to NASA's website and I was like, okay, I want to talk about infrared astronomy. Like, I need a good figure or a good image to talk about what this is and explain this. And so NASA's website had this amazing picture, and I went back because that was 2.5 years ago, and I thought maybe they've updated it since then. They haven't, so we're going to continue to use it. You guys, that's so scary. This is NASA. This is from NASA's website. Like, they have all kinds of things they could have used to explain infrared astronomy, but this terrifying picture of this tiny dog. But whatever. Okay, so we're looking at heat signatures, and so what you would see with your eyes is hopefully this thing on the left. If not, we need to talk. But what you would see in the infrared is you would see heat signatures. So you'd see longer wavelengths of light. And so you would see things like this picture over here on the right, where you have a temperature scale, and then this, I don't know what this is, but this picture here on the bottom, where you have a different temperature scale. So we color these images so that you can see them with your eyes, but they are not purple and red, obviously, right? Or purple, green, and whatever the hell that is, right? So when we look at space, we learn all kinds of things based on the different wavelengths of light that we look at. And so this is a more appropriate astronomy picture, but this is a picture of the Whirlpool galaxy. So this is what you would see with the Hubble Space Telescope. So this is what you're probably used to seeing from all of those pretty space pictures that come from Space Telescope, from the Hubble Space Telescope. And this is the infrared wavelengths of light. So again, it kind of looks like it's on fire because we chose to color things red, because we call longer wavelengths of light redder and shorter wavelengths of light bluer, because red is longer wavelength than blue, and we are not creative. So we have ultraviolet and X-ray to look at really, really hot things in very, very short wavelengths of light, and then radio is longer wavelengths. So I know we've had several talks recently from our radio astronomers about what they can do with radio, but I'm going to focus more on infrared. And one of the premier telescopes that works in the infrared is the Spitzer Space Telescope. So this telescope launched in 2003, and it is still operational today. So I looked this up. I was like, I need to figure it out. So this is actually, today is the, whatever number that is, day that it's in operation. So it was expected to operate for only a few years. So what's happening? Oh, you guys, we're getting Amber Alerts. All right. Everyone's checked their phone. It's okay. Take a minute. Turn it off. All right, so the Spitzer Space Telescope. We actually launched this telescope, and this is kind of an interesting, not to scale image, but here's the Earth. That would be impressive. Here's the Earth and the Moon, and here's Spitzer, giant Spitzer, and the Sun. And so we actually launched it. So it's been following us in our orbit, but it's been falling further and further behind us. And so we actually ran out of some of its coolant. So when we're looking at heat signatures in space, we actually have to cool down the detector because we don't want it to detect itself. Oh my God, you guys, the phones. And so in 2009, we thought that it was going to stop working. It was going to have to, the actual telescope itself was going to get too warm to look at some of these small signatures of heat in space. But we're actually still able to use one of the detectors on this telescope. So it's still functioning. And I was actually, for the past 6 months, if you missed me at Astronomy on Tap, I was at Caltech. So I had a fellowship there. And this is where they run the Spitzer Space Telescope. So Caltech actually had its last call for astronomers to use this telescope, so they all submitted proposals. It was the last time because it's getting too far in this orbit, so it's going to get like over here to where the sun is going to be in the way for us to talk to it, and that's going to be a problem. And so eventually, at some point, it'll come back around the other side, but that'll be in a long time from now, and who knows what kind of condition it'll be in. So they took the last call for proposals, and in fact, that day they definitely had a lot of alcohol at Caltech. So, but things that you can do with, oh my God, this Amber Alert. Okay, I mean, that's sad, but I'm okay. Doing something. Okay, so what we can do is we can look at different wavelengths and we see different things in space. And so again, this is one of those pictures you've probably seen. Does anybody know what this is? Yeah, it's the pillars of creation. All right, so a lot of people have seen this. This is beautiful. This is visible. This is from Hubble. But I'm actually going to show you one of my favorite images of space. In fact, it's like a sticker on my phone. But this is what you see when you look at infrared. So you can actually see through some of the dust. You can see some of these older stars, and you get to see a whole lot more information. And so it's really important for us to look at the universe with multiple telescopes at multiple different wavelengths so that we can learn more about what's around us. And so I'm actually going to zoom out on this image. So that is the pillars right there in the center. And then we've zoomed out a little bit so you can see that there's all of these big bright stars that have kind of carved out this cavity of dust and gas. I know it's big, right? And so you can kind of see that there's like this big area where all of these stars have made this big kind of cavern, I guess, in space where you have the pillars in the center. And so when you look in the visible, this is what the information you have. You can learn a whole lot about how stars form, what kinds of stars are out there, where they're located. But if you just look at that wavelength of light, you can't necessarily know the whole picture. And so what I'm going to show you is one of the coolest animations I've ever seen, because this is incorporating visible light here. But if we look at far infrared, so if we looked for heat signatures or cold dust and gas in space, this is actually what's out there. Yeah, that's pretty cool. So this is exciting science to do, and we don't have a whole lot of telescopes. In fact, a lot of the data for this image was taken by the Herschel Space Observatory, which was run by the European Space Agency, and it's dead. And so Spitzer's on its last leg. So we don't have a whole lot of options here for infrared astronomy, which is kind of a bummer, because what I do is not necessarily look at pretty pictures all the time. Actually, never. But what I do is I study the distant universe. And in order to do that, we need infrared telescopes. And so, does anybody know what this picture is? The Hubble Ultra Deep Field, yeah. So this is a picture of a very tiny spot on the sky. In fact, smaller than like the size the moon extends when you look out in space. And these are almost all, there's a couple stars, but these are almost all galaxies. So all of these little spots of light are galaxies from different distances, different ages in the universe. Oh, hey, that's a star. You can see the little cross pattern. But most of the stuff in this images are galaxies. And I'll move the text out of the way for you. But what we can do is we can actually learn a lot about how our universe evolved. And so what I do is I study some of the first galaxies that formed in the universe, and I want to understand how those galaxies and the universe itself evolved into the one that we live in today. And in order to do that, we need to look as far back as possible. But there's a problem, because I don't know if you've heard, but our universe is expanding. And so what happens is the light that's emitted from galaxies actually gets stretched out as the universe expands. So the distance between things, like if you have a grid point, the distance in your grid points actually expands. And so that stretches out the wavelengths of light that we see. So if I see a galaxy that's emitted blue light, here at the top you see this blue galaxy has emitted some short blue wavelengths of light. Over time, as further and further away it gets, there's this trivia question, right here. It gets stretched out. And so, like I said earlier, blue wavelengths are shorter and red wavelengths are longer. So things that are stretched out to longer wavelengths are called redshifted. Because again, we're real creative. And so the things that I'm looking at are very, very, very far away. And so they're redshifted quite a bit, which means that the blue light or the UV light that has left these galaxies actually shows up to us at infrared wavelengths. And so we can't even see these galaxies unless we have an infrared telescope. And this is kind of like a complicated thing to explain in pictures. And so I have a movie to show you. And so this goes really fast, but I'm going to talk you through it and it's going to loop again. And so if you look at this part at the bottom is like the wavelength of light. So like the shorter wavelengths are over here and the longer wavelengths are over here. And this is like the amount of light emitted by a galaxy. This gray part right here is the amount of light a galaxy emits at any given wavelength. And then the colors are the filters on Hubble. So each Hubble image has this filter which covers this range of wavelengths. And so each one of these corresponds to a picture. So if I take a picture with this filter, it captures all of these wavelengths of light and I get this image. And same for this one here and these all down the line. And so as galaxies get further and further away, what happens is their light gets redshifted. And so what we see is we see this light emitted by these galaxies gets further and further into the infrared. And so what you end up seeing is that this galaxy that's really close, you see a bunch of images at different wavelengths, but as galaxies get further and further and further away, their light gets stretched out into the infrared so far that you only get them in these very, very infrared wavelengths of light. And so what ends up happening is for the very first galaxies that form in the universe, what we see is only light that's very far redshifted. We might only have one image with the Hubble Space Telescope that actually shows this galaxy. And it's very hard to determine if it's like an actual galaxy or just maybe, I don't know, dust or some kind of noise or something like that without more wavelengths. And so this whole process of looking for some of the first galaxies is complicated because you might just have only a few of these filters where your galaxy shows up. And so recently, I wrote a paper about this galaxy I found. And so this is my galaxy, guys. Isn't it cute? Thanks. So you see how I drew the circle just so like you guys can know what I'm talking about. These ones right here are Hubble filters, and then Spitzer, since it's still going. Knock on wood. It's still going. And so these images here from Spitzer are actually kind of zoomed out. So these two bright things right here are actually these two bright things right around the circle because you can see the resolution's amazing. And so this circle right here shows you where the galaxy would be, but we don't see it. So we know how far-ish away it is based on which one of these filters it starts to show up in. And so this is how I find galaxies. I know that's not one of those pretty pictures I showed you earlier, and I'm not lying when I say I don't look at pretty pictures, because that's a galaxy, I promise. That little dot thing right there, yeah, that's my galaxy. And so what we know about this galaxy based on which filter we start to see it in is that the light left this galaxy over 13 billion years ago. Does anybody know how old the universe is? There's so many numbers happening. 13.8-ish billion years old. And so in the first billion years of the universe's history, this galaxy happened somehow. But we can detect it because of this phenomenon where lights get stretched out into the infrared. And so it's really important that we have infrared telescopes, because if we look back in time, so if this is like right now, and then this is back in time, so what you see here is this redshift. So higher redshift things are further back in time, and my galaxy is about this redshift. So with the Hubble Ultra Deep Field, we can just barely see that far away. But if we only have one filter or one wavelength where we see this galaxy, it's really hard to know anything about it. So we need more wavelengths of light, and we need further infrared detections of these galaxies. And with a little bit more Hubble time, we can stare at it longer and see some of these things further away. But there's this thing happening sometime, I don't know when, called the James Webb Space Telescope. Yes. I mean, it was supposed to be my PhD, you guys, but it's all right. We'll be okay. So we can look back after like 200 million years after the Big Bang. So these are some of the first stars and the first galaxies to form. And so what we really want to understand is, where did our galaxy come from? Like, how did we get to be the galaxy that we are? And in order to do that, we really need to understand some of the first things that happen in the universe. And so what I need to do and what I need to have is infrared space telescopes, because infrared light actually gets blocked by the Earth's atmosphere. It's very hard to do this from the ground. So we need to send things to space. And so eventually, oh my God, the James Webb Space Telescope will work, and it will launch, I think, at some point. Right now it's scheduled for March of 2021. And so this telescope needs to be really large, because longer wavelengths of light need larger telescopes to be resolved. And so we need to put a big telescope into space. And so this telescope is actually the size of a tennis court, but we don't have rockets that can fit tennis courts. So we have to fold it up and then like stuff it in a rocket and then launch that rocket into space. And then it's gonna unfold as it travels 1 million miles past the moon. And I swear to you, it's gonna work. If you want any more information about this, I know we've had several talks about it. My boss has come here and talked to you about where in the world is the James Webb Space Telescope. And he sings a song. You guys, it's on our YouTube and it's amazing. But if you want any more information about it, these two websites are great. And my advisor here at UT actually has time on this telescope. So this is an actual image of the telescope. This one right here. Does anyone know what city this is? Okay, yeah, that's where you live. That's Austin. They brought, I don't know, 4 or 5 years ago, they brought a live scale model out to South by Southwest. And this picture is actually the picture that they have at NASA of their telescope. But then this model broke like right after that. So, well, luckily they put most of it together. So we have real pictures. So this is a real telescope. So this is as it was getting assembled at NASA Goddard Space Flight Center in Maryland. Unfortunately, I was there like 3 months before the mirrors were up, and all my friends took selfies with the mirror, and I didn't get to do that. So unfortunately, but right now it is being put together at the Northrop Grumman facility right outside LAX. And since I said I was in California recently, I went to go see it. So I got to see like the whole shield and the mirror as they were putting everything together. But they wouldn't let me take pictures because, I don't know, security or something, whatever. But it's coming together. It's going to work. And it's going to launch soon. I don't know. But this telescope is going to be able to look further back in time. And this is what we really need. Because like this is what our Hubble Ultra Deep Field, this isn't as pretty of an image as the one I showed you earlier. But this is a example of what Hubble can see in a deep field. So if we took Hubble and we stared for a long time, this is how sensitive it could be to distant things. But this is what JWST is going to be able to do. And so there's a whole lot more information out there that we really need infrared telescopes to do. And so learning more about our early universe is a very important thing to understand how we got here. And that's what I am studying now. And unfortunately, my PhD will be something else. But coming soon, the James Webb Space Telescope will tell us a whole lot about our early universe and how we got here. So I'm just going to play this video real fast that I've seen a million times, but like you guys have probably seen too. But that's the end of my talk, and we can take questions while that plays. So thank you.
Thank you, Chaos Cloud. So we have some time for questions. Right here in front.
So how do you distinguish between something redshifted versus something that's just emitting information?
So the question is, how can we tell if something is redshifted or if it's just red? And that's a great question. In fact, that's a huge problem. It's really difficult. And so what we need to do is take multiple pictures of it. We need multiple telescopes with multiple wavelengths in order to determine if something is actually just emitting a lot of red light, or things like that would be galaxies that are really dusty. And so dust emits kind of like in the red wavelengths. And so we need to be really sure when we're looking with really deep data. So we need to point telescopes for a very long amount of time to make sure that we can distinguish between something that is actually pushed out very far in the redshift range, or if it's actually just something that's kind of dusty. And I wish I had a plot to show you, because I'm a scientist, so we like plots. But yeah, it's actually a very complicated thing, and in most of the things that we write about, that is a big question that we get from all of our peers as to whether or not it's real, or if it's just really close and really dusty. So that is a problem.
Yeah, in the middle right there.
Yeah. So you mentioned that the universe is constantly expanding. Is it true that at some point or another it might actually go inward?
So the universe isn't necessarily constantly expanding. In fact, the expansion of the universe is accelerating. And since we're astronomers, we don't name things well, and we call this dark energy. So something is adding energy into the universe that's making the expansion of the universe speed up. So it's not likely that the universe will collapse again, since it's actually everything is moving further away from everything else, even at an accelerated rate. And so the something major would have to happen for that expansion to slow down, stop, and then turn back around. So it's not very likely as far as we understand.
By the poll.
Could the Hubble not have been fitted with a deep IR filter?
So the question is if the Hubble Space Telescope could have been fitted with a deep infrared filter. It could have been, but if you looked at those Spitzer images, those resolutions were really low. So like if you look at like an old TV versus like a 4K TV, it's a very different experience. And what you need is that you need actually a bigger mirror. So your resolution, your ability to resolve things is reliant on the size of your telescope. And so Hubble is not big enough for a longer wavelength filter to have a very good resolution. You need more light gathering power, so to speak. So you need a bigger telescope to have a longer wavelength filter. That would be something that you could even, resolve the difference between different galaxies.
Any last questions? Oh, okay. Yeah, last one right there.
How do you test the mechanics of the telescope? Like
Do you mean this one? So the question is how they test the mechanics of the telescope. And a lot. They do that a lot.
Very carefully?
So they hopefully very carefully. They actually open and close a bunch of the things. I think there's something around 3 to 5 redundancies for every single movement that this telescope makes. Hubble was launched, and it's only like 200 and some odd miles above the Earth's atmosphere. And so we could go fix it. This one will be 1 million miles away. So they've tested every single movement this telescope makes multiple times. There's multiple things that can move each part of it in multiple ways. And the reason it's actually delayed right now is because one of those things malfunctioned, and they wanted to make sure that it was actually deploying this bottom part, the sun shield, in an appropriate manner. And so that's why they're delaying it, to make sure that this motion is actually working properly.
Another thing, if you've ever been to the Goddard Space Flight Center, they also have this big old sound like speaker room. So it's like this thing's going to be attached to a rocket and needs to, sustain all of these vibrations as it goes from the Earth's surface up into space. And so they put the whole spacecraft into there, and they just like play these really, really big, loud noises. You need to close it. It's like super thick walls, because you would like die, if you listen to it. So yeah, that's pretty cool. But let's thank Rebecca again.
Thanks, guys.